Okay, let's discuss two more examples of graphs of rational functions. Okay. Okay. Assume this rational function is two x squared minus 5x plus 2 over x squared minus 4. So step 1, we try to determine the domain. To determine the domain, you need to factor it. To factor it, you will get 2x minus 1, x minus 2, and over x minus 2, x plus 2. Okay, so that's the factorization. From the factorization, you can see the denominator, when x is 2 or x is negative 2, the denominator is 0. So the domain is the set of all x. X is not equal to 2, x is not equal to negative 2. Okay, so this is the domain. And step 2, the lowest terms. The function, the rational function, the numerator and the denominator, they have the common factor x minus 2. So basically you can cancel x minus 2. So the lowest terms of r of x is equal to 2x minus 1 and x plus 2. So this is this is the lowest term. You have to cancel stuffs. Okay, then step 3, we look for intercepts. Y-intercept. Y-intercept r of 0. You let x be 0. It's equal to 1 half, negative 1 half. Let x 0, so 0 minus 1 over 0 plus 2, negative 1 half. X-intercept. X-intercept is a solution of r of x equal to 0. R of x rational function is equal to 0 if and only if only the numerator is equal to 0. 2x minus 1 is 0, so x is positive 1 half. Okay, so this is a y-intercept, x-intercept. And then let's study the behavior near 1 half, near the x-intercept. Near x equal to 1 half, what do we have? We have, okay, r of x is almost, x equal to 1 half comes from 2x minus 1. So you keep 2x minus 1. And over x plus 2, over x plus 2, x is 1 half, so over 1 half plus 2. 1 half plus 2 is 5 over 2, so you flip it, it's 2 over 5. So this number, put it here, it's 2 over 5, which is like, what's this? It's a 4 over 5 times x minus 2 over 5. So it is a linear function. Okay, so that's the behavior near the x-intercept. Okay, then next we study the vertical asymptote. Vertical asymptote comes from the denominator of the rational function in lowest terms. So here, you don't go back to the original one. You study the lowest term rational function. So x plus 2 is 0. X is negative 2. Okay, x plus 2 is 0. X equal to negative 2. This is the vertical asymptote. Right? And then we study the horizontal or oblique asymptote. horizontal or oblique asymptote. Okay, so this function is not a proper rational function. It's improper. Proper numerator has smaller degree. Here they share the same degree, so it's not proper. It's improper. And then let's try the division. You divide the numerator by the denominator. So you divide 2x squared by x squared, you got 2. So 2x squared here is 0x and minus 8. Negative 5x minus 0x is negative 5x. 2 minus negative 8 is plus 8. It's negative 5x plus 10. So what is the division? The division r of x is equal to 2 plus the numerator, the remainder over the original denominator. Right? So you have a number, then it means y equal to 2. Y is equal to this expression. Y equal to 2 is the horizontal asymptote. So you have a constant is horizontal. You have a linear function is oblique. Okay, so horizontal horizontal asymptote. And step 7, the zeros of the numerator and the denominator. We use this to add additional sample point and try to sketch the graph. Okay, so the zero of the numerator here, from the lowest term, 2x minus 1, so you get x is 1/2. And 0 of the denominator, you get x equal to negative 2. So you have 1/2 and a negative 2. 1/2 negative 2, see here, you have negative 2 here, you have 1/2 here. So you have 3 intervals. Okay, so far we don't do the evaluation. Let's see if we can sketch the graph or not. Let's try to collect all the information we have known and see the basic picture. Okay, x and y. So the negative 2 give you the vertical asymptote. Negative 1, negative 2, vertical asymptote, the dotted line or the dashed line. And the y-intercept, negative 1/2. Negative 1/2. This is negative 1. This is negative 1/2. This is a point on the graph. Negative 1/2. And the x-intercept, x-intercept is 1/2. X-intercept is 1/2. This is 1/2. And the vertical asymptote, we have a vertical asymptote. Horizontal asymptote, y equal to 2. Y equal to 1, y equal to 2. Okay. Whenever you have horizontal asymptote, you want to see if the graph intersect horizontal asymptote or not. To do that, you let r of x, 2x squared minus 5x and plus 2 over x squared minus 4. You let the rational function equal this number 2. Okay, you copy the rational function, you let it equal the horizontal asymptote. So we find intersection. We want to know we want to know if the graph crosses a horizontal asymptote or not. Okay, so the solution, 2x squared minus 8. So it's a negative 5x plus 2. You cancel 2x squared is equal to 8, negative 8. So negative 5x is negative 10, x is 2. So when x is equal to 2, the graph intersect the horizontal asymptote. Okay, so 1 and 2. So this number 2 will be used later. Okay, very good. Let's check. Do we have a mistake or not? Let me see. We have 1/2 and I don't want to make mistake. This asymptote. Sorry, the y-intercept negative 1/2, x-intercept 1/2. Yeah, it's correct. There's no mistake. Well, let's see. But you see here, we have some strange stuff. X equal to 2. X equal to 2, but 2 is not in the domain. Yeah, now we see the mistake, the problem. 2 is not in the domain. So it means if 2 is not in the domain, it means there is no intersection. Okay, so there is no intersection between the graph of function and the horizontal asymptote. Okay, and next, let's see what is the information we still miss. Here, this near the 0, we have a segment. It's like this. It's like this. Okay, so it's limited. So we don't have enough information. Let's use this 3 segments to add additional points. So here, less than negative 2. Let's pick up negative 3. You evaluate r of a negative 3. You will get it is equal to 7. Just put the value here. Where? Here, yes. Negative 3, yeah, it is equal to 7. And between them, negative 3 here, is equal to 7. It's very tall. And between them, you can pick up 0 is already computed. You can pick up negative 1. This is a negative 2 and negative 1. You evaluate negative 1, r of a negative 1. R of a negative 1 you computed, it's a negative 3. It's someplace here. Okay, and in this place you can check 2 is not in the domain. You can check 1, you can check 2, whatever. You can check 1, you can check not 2. You can check 3 or 4 or 5. So for example, if you check 1, what is 1? R of 1. R of 1 is 1 over 3. And R of 2, 2 is undefined. R of 3 is 3 times 2, 6. 6 minus 1, 5. 3 plus 2 is 5 also. It's equal to 1. R of 3 is equal to 1. So 2 is undefined, so 3 is here. 3 is equal to 1. Okay? So now let's try to connect them. So these two things, you connect it like the straight segment. And here you also connect the like straight segment. And then it will approach to the horizontal asymptote. And this one, you connected them, and they will approach to the vertical asymptote. And remember, there's no cross, no intersection, no cross, okay? And this part, you only have 1 point. When it is close to the vertical asymptote, it has to go to infinity, positive. When it is close to the horizontal asymptote, you see, it has to be like this. There's no other choice. If you want, you can of course estimate evaluate the function at -4. You will get something like this. So anyway, it looks like this one. So there are two branches, this branch and this branch. The final thing, the difference between this example and the last example, you have to put circle here. The circle means the function is undefined at 2. Remember, 2 is not in the domain. After you finish the process, you sketch the two graphs. But remember, this graph is the graph of these lowest terms. It's not the graph of the original function. The original function is undefined at 2. So you must put a circle there to say the function is not well defined at equal to. At x equal to. Okay, so that's an important thing. So x cannot be number 2, so you put a circle here to tell the difference between the graph of the original function and the graph of the lowest term. Okay, that is the purpose I presented this example. Okay, so whenever you cancel some terms, the final step, you have to remove, possibly you have to remove some point from the graph. Okay, let's see. Next, we study the problem from the different direction. We want to construct a rational function from a given graph. Okay, so construct a rational function from the given graph. What is a given graph? A given graph is like this. At -5, you have a vertical asymptote. At +2, you also have vertical asymptote. At 2, you have y equal to 2, you have a horizontal asymptote. And this is 5, so 1, 2, 3, 4. Okay, at this point, it touches the x-axis. Here it intersects at this intersect at y equal to -2. This is -2. This is -2. And this part is like this. And another thing is that this is 2, 1, 2, 3, 4, 5. At 5, the graph is like this. This is the given graph. The given graph. We want to construct a rational function with this given graph. Okay, so let's study the possibility. So first, vertical asymptote. The vertical asymptote comes from the zeros of the denominator, right? So whenever you have -5, x equal to -5, x equal to 2, whenever you have such stuff, you move -5 to the other side, you get x plus 5. You move 2 to the other side, you have x minus 2. So it means the x plus 5, x minus 2 are factors of the denominator. X plus 5, x minus 2 are the factors of the denominator. And another interesting property, when we discuss the vertical asymptote, we mentioned that there are two possibilities. One possibility is like this way. The other possibility is like this way. They either approach to the same infinity or they approach to a different infinity. For this one, it approaches a different infinity. One side approaches positive infinity, the other side approaches negative infinity. It implies the power of the corresponding factor is odd. If they approach the same direction, either above or below, like this approach to the same direction, it implies the power here is even. The smallest even power will be 2. So why don't we just put the number 2 here? We'll construct one rational function. Okay? So far, let R of x be P of x over Q of x. Then Q of x can be written as x plus 5, x minus 2 squared. Okay, so that is the property. That's a Q. What about P? What about P? P gave us the x-intercept. So let's check. There's one intercept of 5. There's another intercept of -2. The intercept are the zeros of the numerator, are the zeros of the numerator. X-intercepts are zeros of numerator. So this one, the graph cross x-axis, the multiplicity is odd. This one, the graph touches x-axis, the multiplicity is even. So we will put x minus 5, that corresponds to this 0. X plus 2, it corresponds to the 0, -2. It's even power. This is odd power. Okay? So now what we have? We have R of x is equal to numerator over the denominator. So what do we have? What do we have to? What have we studied? We have studied the vertical asymptote, the zeros. We still don't study the horizontal asymptote. Horizontal asymptote means when you divide the numerator by denominator, you see here, when you divide the numerator by denominator, the ratio, the quotient should be a number. If you expand this and do the division, you will see that this one has a coefficient of 1, the quotient of 1. So in order to get number, this is 2, y equal to 2. You multiply the numerator by 2. You will see that with this coefficient 2, the quotient is 2, and the remainder is something else. Okay? So we multiply it by 2. This 2 comes from the horizontal asymptote. Horizontal asymptote. Okay, so that is the constructed example. You can check that the graph, this function satisfies this graph. This is one possibility. It's like we start from a graph, we design the corresponding rational function. So this is the opposite direction of the similar problem. How do we connect the algebraic property with a geometric observation? Algebraically, it touches the x-axis, the power is even. Algebraically, you see here, they approach the same direction. same negative infinity or same positive infinity, the corresponding power is even. If they have different infinity, like one is up, one is down, one is up, one is down, then the corresponding power is odd. Okay? So there are many examples. You must do one or two of them at least to get the idea of the graph of rational functions. It's not that simple, so you have to collect all the information you know about the rational functions. Okay, so do the exercise. Okay, so here we really finish the section 5.3. The section 5.3 is very comprehensive. Try to do problems. Don't just take for granted. It's very difficult. Okay, now let's move to a different topic.